So yeah, so please, Micheline, thank you very much for joining us today.
Thank you, Devira, and hello, everyone. My name is Micheline Soley, and I work at the Yale Quantum Institute. And today I'll be talking about developments that I've made in ultracold collisions and global optimization, and approaching the problem of simulating quantum dynamics and high dimensionality. So my talk today will have two parts. So in the first part, I'll be talking about an algorithm that I developed with Victor Batista and Paul Bergold which we call the iterative power algorithm, and it's applied for global optimization. And then in the second part, I'll be talking about a method that I developed with Rick Heller and Cobra Nassiri Avenaki to develop complex absorbing potentials for simulation of ultracold quantum dynamics that are nearly free of anomalous reflection effects. So to begin, the first part of my talk will concern an algorithm for global optimization. So global optimization is the idea that if we have some function we want to optimize, we want to find either the lowest or the highest point on that function. And so global optimization has many applications in chemistry and physics and beyond. So here at the Quantum Center in Toronto, for example, people are interested in looking at optimization for example, finding for like variational quantum eigensolver, which involves a classical optimizer, or finding ideal quantum optimal control pulses. And global optimization can also be used for a wide range of applications as well. So for example, sometimes prime factorization is used for cryptography, for like hiding secrets that we pass through each other on computers. And that problem of prime factorization can be solved by a global optimization problem. And in addition, at the Yale Quantum Institute, they're using this kind of hybrid cavity qubit system, which is a kind of quantum computer. And in order to control the state in the cavity, so this bosonic computing structure, we use optimization to find out what is the ideal pulses that would drive the quantum computer into the desired state. And so I won't talk about it today, but one place where global optimization is very important in my research is research that I'm doing with Steve Girvin in trying to be able to simulate a Hubbard lattice. So there are, for example, fermions in two different sites and how they move according to the Fermi-Hubbard lattice Hamiltonian, and how can we figure out what kind of pulses would you send into a hybrid qubit oscillator quantum computing architecture to try to achieve, try to have a quantum simulator of the Hubbard lattice. So if you're interested, I could discuss that later. So the problem with trying to find these global optima of functions is what we call the cursive dimensionality. So for example, when we're trying to use optimization to find ideal chemical structures, it turns out that as the number of the dimensions of your optimization problem increases, there's also an exponential growth in the cost of the memory needed to represent that system. So for example, let's say that we want to represent a one-dimensional Gaussian, for example, in like a quantum dynamics simulation. If we look at that Gaussian at 2 to the 8 different values, at 2 to the 8 different positions on the x-axis, and we save each of those as floating point numbers in the computer, this would require 2 kilobytes of memory. So it's still very manageable. And if we look at the 2D system, and again, so if we're looking at a 2D Gaussian, and then we divide the x-axis and the y-axis in 2 to the 8 different points, now it takes 0.5 megabytes. So this is still plausible. But if we go to 50 dimensions, now it quickly it's more than we could simulate on our personal computer, and it's often more than we could simulate on even high performance computing devices. So we need some kind of solution to be able to perform global optimizations of these kind of functions efficiently. So one way that I've developed in the past with Andreas Markman and Victor Batista is an approach to optimization called the diffeomorphic modulation under observable response preserving homotopy approaches. So this is a big term, but basically what we're doing here is that we say, let's say we have a function to optimize. So say this green line here, or the blue line on the right. And we want to find what the lowest point on the function is. One way we can do this is by initializing a wave function in that, treating the function we want to minimize as a potential energy surface, and then initializing the wave function in the potential energy surface. And then we can find out that by finding and applying some optimal electric field to this particle, the particle will eventually fly above any sorts of barriers and then fall into the global minimum part of the potential. And then by taking the expectation value of the position of this particle, we can find out where the global minimum is. So basically, this is a kind of quantum dynamics way of finding the global minimum of a potential energy surface. But this has a technical problem that in order to find the global minimum of the potential energy surface, it depends on what you chose as your initial condition of what is that initial wave function that we started with, because it requires that there be some overlap between this initial wave function and the final wave function that's in the global minimum. So we wanted to develop a more general way that we could do this that doesn't have the cursive dimensionality. And so what we came up with is the iterative power algorithm. And so to give a sort of general overview of what this method is, again, we choose the function that we want to minimize. So here we use this jagged function here in yellow, and we want to find the global optima, which are these starred points. Instead of starting with an initial wave function that sits just in one part of the potential energy surface, now we have a uniform superposition, a uniform distribution that's one everywhere in the potential energy surface. And then we iteratively apply some kind of weighting function so that parts of the wave function that aren't above global minima decrease, and parts that are above the global minima increase, so that in the end, we're left with a wave function that's peaked every time we're at a position of one of the global minima. And one might say, if we start with an initial wave function that's evenly distributed over the whole possible search space, so all the possible places where the minima could be, that sounds like we might have to evaluate the function everywhere in the search space. And that would have the cursive dimensionality, because as the dimension increases, you've got more and more points you have to sample. So the way that we get around this is, instead of using some kind of grid-based implementation where you're evaluating the function at every point, instead we're using this kind of low rank representation, which is called a tensor train, or specifically a Quantix tensor train network. And so what this basically does is, let's say we have a 2D element array. So let's say we have some sort of vector with 2 to the d different elements. So, and we want to reduce the amount of memory that's needed to store this, this list. So what we do is we reshape this vector into a 2 by 2 by 2, etc. tensor. So for example, these 8 blocks would be rearranged to be 2 blocks in each direction. And according to the Quantix tensor train decomposition, what you can do is, instead of saving the value of each of these blocks, you can find out different, what are called tensor cores. They're sort of like different vectors, different pairs of 2 blocks that you can save the value that you have in each of those 2 blocks. And then take an outer Kronecker product that of those different sets of 2 blocks, which is illustrated on the left. And then take a sum of these different kinds of products and this will actually reduce the cost of saving all the data. So basically you don't have to save the data in every point. And in our IPA algorithm, our iterative power algorithm method, we use this efficient memory way of representing representation to represent the quantities of like the density and the potential to avoid the cursive dimensionality. So to be more specific now, instead of having to evaluate 2 to the d different points, so it's an exponential cost in d, this special format allows us to save the value only in 2d to r squared points. So now you can see instead of an exponential scaling in the dimensionality, which is the cursive dimensionality, now it's only a linear scaling. So we've vastly decreased the amount of storage requirements for this function. Now, it's important to note that this scaling still depends on R, which is the maximum rank. And that basically tells you how many of these terms do you have to save. So how many of the outer products of quantities do you have to save? So this is only beneficial if R is a small number. And it turns out that actually many different problems in different fields, like from like aerodynamics and like drone design all the way to chemistry, actually turn out to be often low rank systems. So for example, looking at protonation of water or hydrogen bonding in DNA or Zundel ion systems, often these can be represented in terms of system where R is low. So we get very advantageous scaling with this context tensor train representation. And another really interesting thing about context tensor train is you'll notice that when I rearranged the blocks, they were like 2 by 2 by 2 by 2 systems. And the idea of looking at systems that each have 2 elements looks a lot like a qubit, where you have 2 different possible states. And so this actually shows, it turns out that the context tensor train representation I was talking about actually features a lot of similarities with qubit-based quantum algorithms. Like for example, both types of methods yield an exponential improvement in data sparsity. And I'll show that the method that I developed, iterative power algorithm, actually has some similarities with the Grover's algorithm. Both use the idea of efficient initialization, recurrence relations, and measurement. And as I'll show in the results, it also, you can get like quantum-esque speedups by using the context tensor train method. And so this suggests that context tensor chain representations in general could be used to develop classical computing analogs of quantum algorithms like the one that I discuss here. And so now I'll discuss sort of the finer points of how the iterative power algorithm works. And so the first thing we do is that we take the cost function that we want to minimize. So for example, we might want to find the lowest point of a potential energy surface for a molecule, for example, to figure out what is the optimal configuration of the molecule. So we represent that as a potential energy surface in our method, and we'll call the global minimum that we want to find X star. And now we initialize a probability distribution in that potential as a context tensor train. And so basically this means that the probability distribution will be 1 everywhere in the search space. And we use, since this is a context tensor train, we don't have to evaluate the density everywhere, but instead you can have it in one of these compressed low rank objects. So the next part we do is try to isolate the global minima of this on the surface. So we define what we call an oracle in an analog to like a quantum oracle. And here we use the example where the oracle is e to the minus beta v. So this is directly related to the idea of the imaginary time propagation method for infinite mass. And so what this does is when we apply the oracle and renormalize it, what happens is that where initially the uniform distribution was just flat, what this weighting function does is that when we're at lower parts of the potential, it starts to peak above the minimum, and then it decreases everywhere else. So as an example, I'm showing here on the bottom right what happens if you use that oracle with the parameter beta equals 1 in some potential where the minimum is 0 here. So you see after one application, it starts developing a peak. And if you do it enough times, after 500 iterations, it's a Dirac delta function directly over the global minimum. So now basically the position of your wave function shows you where the global minimum is. So if we were going to try to figure out where the Dirac delta is by evaluating the density everywhere, we'd be back to having the problem because we would have to evaluate the density at every point. So instead, what we do is we find that global minimum by using a quantum style measurement. And so if we have only one global minimum, then the position of the global minimum is the expectation value of the position of that wave function. So that's the example shown here. So we just take the expectation value of the position. Now, if we have two minima, we can still figure out where the positions are by first finding the average of the position of the two minima. So just by taking which turns out to be the expectation value of the position of the density. And then we can apply a Heaviside function or step function that sort of blocks our view of one of the densities, so say the left one. And that would leave us with the part of the density on the right. And an expectation value of the position of that would show you where the location of that global minimum is. And you can repeat the same kind of method with the step function flipped to figure out where this other minimum is. And it turns out you can actually continue doing this for any number of global minima. And so, for example, if you have an arbitrary number of global minima, we use what we call the ramp method. So, so first we perform IPA, and that gives us what we call a Dirac comb, which is just a density that's 1 at all position of all of the global minima and 0 elsewhere. And so then what we do is we say that's our new initial density. So now we have the density being 1 at the position of all the minima, and we optimize, we run IPA again with a ramp potential. Here we use a linear ramp potential. So what that's going to do is isolate the global minimum with the lowest position. And then we can then we can find the expectation value of the position of that, part of the density to get the location of the global minimum. And then we can use the Heaviside function, which sort of blocks our view of that minimum. And we can keep repeating it to locate all of the minima until they're all gone, and we can identify each one. So one interesting thing is that we evaluated how quickly this will converge. And the way that we did this is by noticing that you could calculate the convergence of IPA in the same way that you calculate the convergence rate of Grover's search algorithm. And so the way that this is done is by considering what happens if you apply the oracle for one step. So this is shown on the right. So if you apply the oracle for one step, whereas before the density was 1 everywhere, now it'll be maximized at the global minima with lambda 1. And here, just for a simplified case of the convergence, we assume that everywhere else, the oracle be lambda 2. And so when we apply this oracle to the original uniform distribution, we end up getting k times, we end up getting this expression. And what this does is amplify the amplitude at the global minimum by lambda 1 over lambda 2. And by using the idea of the fact that the norm of the whole density is conserved, we're able to figure out what the value of the density is at the global minimum, which gives us this expression. And just like in Grover's search convergence checks, we're interested in how many times would you have to apply the oracle in order to give you 50% of your amplitude at the global minimum. And so we compare 1/2 to the value of this density. And so we get that this is the number of required steps for IPA to locate the global minimum. And you can see that it's only logarithmic in the size of the search space N. So to show that the applicability of this algorithm, we first apply it to hydrogen bonding in DNA. So here, we're not optimizing the backbone, but instead only optimizing the distance between different base pairs of adenine and thymine in DNA. And this system can be represented as a double well, where the global minimum corresponds to the favored isomer, and the local minimum is the less favored isomer. And the potential that's given for a sum of all of these different base pairs is given by a sum of different double wells. And this turns out to be a very low rank potential. So it's good for showing that the method works for low rank potentials. So after applying it, we look at what happens in the error of the located global minima as a function of the number of iterations, the number of applications of the oracle. And we can see that very quickly it identifies the global minimum well, and very quickly identifies the global minimum to a high degree of accuracy. And on the right, you can see the optimized density in a 2D cut for a 50-dimensional system. And you can see that it correctly locates the global minimum. And it turns out that the example that we show, here we're looking at 50 different adenine-thymine pairs. And we're looking at 2 to the 8 possible positions in each of those dimensions. So this is effectively IPA finding the global minimum energy structure in 400 dimensions, and with many different possible minima. So this would be impossible with a straightforward case in which you enumerate all the positions. But one concern is that this was a very low rank system. So the question is, would this method also work on a surface, the potential energy surface that's higher rank? So what we thought would be an interesting problem that sort of quantum computing ties to look at is the problem of prime factorization. So this is the idea of taking some number and finding the prime factors. And this is essential to RSA cryptography today. Now, the prime factorization problem can actually be mapped to the problem of global minimization, because the prime factors of some number n are also the global minima of the function n mod p, where p is the set of primes. So here I'm relating prime factorization of 187 to global minimization of this problem. So you can see that here the global minima are at 11, 17. So IPA works very well here. So here we take our original potential energy surface and we reshape it into 2D as part of the Quantix tensor train method. And we start with our initial density, which is 1 at all possible prime factors. So after only 1 iteration application, you start to see the global minima peak out. And then at the final density, now you can see you've got isolated the two global minima. But this was a sort of small prime factorization problem. So we thought, what if we've got like a really huge number that we want to factorize? And this number we chose because it's known to have small prime factors because of the limitations of today's tensor train algorithms. So we said, can we find the prime factors of this number with 2,773 digits? And it turns out we can. So these are the prime factors of that number. And here you can see that the final density has nearly all of the density is at all of those prime factors. And then we use the ramp method and we isolated all of the different prime factor values. Now, luckily RSA is not in any trouble at this point. So cryptography is not in any trouble because you can see all of these have small values. But with better tensor train tools, we would be interested in applying these to numbers that have larger prime factors. So In addition, we looked at the rate at which it converges to see how this compares to our prediction. And we see that when we look at the amount of time IPA takes to locate prime factors of numbers that are biprimes, which means numbers that are made up of products of two primes, we see that the execution time scales logarithmically, which is in agreement with our prediction, and may be comparable or better to the rate limiting steps, the most difficult steps of some of the foremost quantum approaches like Grover's and Shor's. Grover's search algorithm and Shor's prime factorization method. So this suggests that the quantics method we're using avoids the cursive dimensionality for these systems and allows us, like as in the 400D case, to look at problems that would be difficult or impossible on existing classical high performance computers. And it also allows us to develop IPA as a way to bypass the limitations of traditional optimization methods. So going forward, it suggests different possibilities for developing efficient algorithms for physics and chemistry and classical computing. So I'm currently working on different methods for applying the same kind of global optimization approach to finding optimal structures for molecules. I'm using tensor trains to simulate dynamics of different chemical systems and looking at X-ray spectroscopy and Chebyshev propagation in high dimensions. And I've also been working on development of new quantum algorithms that have classical inspiration, such as finding local eigenstates. And in addition, as sort of a culmination, we're looking at an idea of developing, so IPA had sort of quantum origins and we turned it into a classical algorithm. So now we're looking at taking that classical algorithm and making an efficient quantum algorithm. So we've developed a circuit and analyzed its efficiency for trying to put IPA back on a quantum computer. So basically the bottom line is that this invites a search for quantum inspired tensor train algorithms and in turn tensor train inspired quantum algorithms. So I'm now going into the second part of my talk.
So sorry, just there were a couple of questions in the chat.
Yeah.
People want to jump in and maybe before we move. Amar, do you want to ask your question or wait to the end?
That's okay, I can wait till the end.
Okay, sure. So yeah, so let's continue.
Thanks.
Sorry.
No, thank you. So going into the second part of my talk, switching gears, now I'll be talking about reflection and ultra-cold collisions. So this research was interested in how can we improve the accuracy and speed of ultra-cold dynamic simulation. So currently there's interest in ultra-cold chemical reactions, which are the idea of chemistry happening below 1 millikelvin. And so the production of ultra-cold molecules has many applications, from different types of beam sources and spectroscopy to creating quantum simulators. And these ultra-cold reactions are really interesting because they're so deep into the quantum regime. And so they rely on using quantum dynamics to accurately simulate them. But for the reasons I mentioned having to do with the cursive dimensionality, often these kind of quantum dynamics methods are expensive. And in addition, ultra-cold chemical reactions often rely on this method called complex absorbing potentials. So here, for example, you have some sort of wave packet and there's some potential. And you want to simulate what happens to the wave packet. And so what's often done to simulate an open system is to have an imaginary potential at the boundary. And so what this does is that the wave function comes through, interacts with the potential, and then it's absorbed by the boundary, and you don't look at what happens to the wave function once it's passed. And these equations on the right show that the potential is then a sum of your potential you want to study plus a complex potential with real and imaginary parts. And what happens is that, for example, if you look at split operator Fourier transform dynamics of the system, you can see that if you have an imaginary part to your potential, what it's basically going to do is reduce the amplitude of the wave function when it hits the potential. And so basically the effect is that now you've got your your wave packet traveling through the real potential, and then it gets absorbed at the imaginary potential and it's gone and you don't monitor it anymore. And it's what's pretty interesting is that this isn't just used in like chemistry or chemical physics, but it's also used in other open systems. So these aren't areas of my expertise, but it's also used, it's called optical potentials in the field of nuclear physics, where they also use absorbing potentials in an interior region. And it's also used in optics, where it's called the perfectly matched layer. And you might notice that on this image, perfectly absorbing layer has a question mark. And that's because they're not so perfect. What happens is that sometimes you get reflection from the potential that's supposed to absorb your wave function. So in these unphysical reflections, your wave function comes through, and then instead of getting absorbed by the imaginary potential at low energies, it actually reflects back, which is unphysical, and it's going to start interfering with what the region you're trying to study. So the usual way to get rid of this problem is to choose broader and broader imaginary potentials, because this is due to an impedance mismatch issue. But you can see that as you're broadening your potential, you're increasing the amount of space that you have to simulate. So the broader your potential, the more cost, and you have the cursive dimensionality, so it's going to get really expensive, which is especially a problem in ultra-cold reactions where the energy is low and this impedance mismatch is high. So this has been a problem for 30 years, which is since the inception of complex absorbing potentials. So you can see that for the past 30 years, people have been talking about what can we do to get rid of this anomalous reflection so we can use this powerful approach. And often these methods turn out to be quite complicated and involving many different kinds of optimization steps or different tricks, and they can be quite complicated. So our idea was we wanted to make a simple physical approach that would get rid of the reflection. And the idea for our approach came from that we see that quantum particles in a complex absorbing potential reflect in two different ways. So one, they reflect off of the imaginary potential. So instead of absorbing, they experience this kind of impedance mismatch where the high energy parts of the wave packet go through and the low energy parts reflect back. And they also experience impedance mismatch from the real potential. And this is called quantum reflection. In recent years, the picture of how this happens has changed, but the general idea is that if you have a wave packet at low energy, even if there's no barrier and no imaginary potential, if it's low enough energy, your wave packet comes through and then it bounces back, even though it looks like classically there'd be nothing to reflect it. And so we realized that these are both essentially quantum problems, that if you had a classical particle in your cap, it wouldn't do the same thing. So if you could somehow make the quantum trajectories in the cap behave classically, you could be able to reduce these unphysical reflections. So like, if you think about it, a classical particle, if it goes through an absorbing wall, it would just go through. There's nothing to drive it backwards. And same, if you're in a real potential with no barriers, then the classical particle would just go through unimpeded. And it's not just classical, but if you use semi-classical mechanics, you can often represent wave functions in terms of a sum of different classical trajectories. So semi-classical particles would do this too. So what we do is we create a physical approach to getting rid of the reflection. So we take advantage of the different behavior of quantum and classical particles. So we have the quantum particle behave quantum mechanically in the region we want to study, so in the real part. And then when it gets close to the cap, it sort of behaves more classically. And in that way, we don't get reflection from the complex absorbing potential, but still get the physics, the quantum physics of the physical part of the potential. And so the physical approach is that we carefully accelerate the particles so that they behave more classically near the cap. And then we reel them in like a fish and absorb them into the imaginary potential. And so the details of how this works is first we reduce reflection from the imaginary absorbing part of the cap. because we know that most of the reflection is going to come from the low momentum, low energy particles. So what we need to do is have a negative real part of the cap that accelerates these particles so they move faster and reduce reflection from them. And so, and ideally we want this to be reflection-free potential so it doesn't itself generate reflection. And so what we do is we use this kind of Coulomb potential where we have an exponential switching function that slowly turns your original potential into a Coulomb potential in the region we're going to put the imaginary potential. And what's cool about the Coulomb potential is that the Coulomb potential is actually reflection-free in 3 dimensions. And this is because a 3-dimensional Coulomb potential can actually be mapped to a system of harmonic oscillators via what's called the Kustanhamo-Stiefel transformation. And a set of harmonic oscillators can be, is semi-classically exact. So it's the same like the pseudo time propagator for it. So some quantity that describes its motion is the same both classically, semi-classically, and quantum mechanically. So since the Coulomb propagator, specifically its pseudo time propagator, can be directly related to the harmonic oscillator, it too is semi-classically exact and therefore reflection-free. It's because it behaves semi-classically, it behaves classically, and there's no reflection. So the second part is now we know there's no reflection from the Coulomb potential, but we still could have reflection from the switching function we use to turn it on. So this is like a little bit of reflection on from the real potential itself. And so what we do is we add what we call WKB corrections that ensure that at one specific energy, so in our case, maybe at the lowest energy that we're studying, the quantum particle will behave classically. And so basically we're trying to make the solutions of the Schrödinger equation and the same as WKB wave functions. And so that basically just means adding a tiny term to the potential, which is very small. So it's a small perturbation, and it ends up looking a little bit like this on the real potential and the imaginary potential. And Rick Heller affectionately calls these rabbit ears. So you can sort of see one floppy ear down and one regular ear up. So the reason this works is because semi-classical WKB solutions are themselves built on classical quantities. So they're in some ways reflection-free. So this is the Wenzel-Kramer-Boolean WKB wave function. And you can see that this part actually turns out to be related to a classical probability density. And this part is related to a classical action. So it's hiding some sort of classical behavior. So if we put this together, if we look at first our original cap without any kind of corrections, it looks like on left. This is a standard Wood-Saxon potential, which is often used for this application. So when we add our corrections, it looks like on right. So now we've got our Coulomb potential, you can see here, and there are rabbit ears, our small perturbations, and you can see they're quite small. And so we find out that this approach at lower energies, which is where the problem of reflection is biggest, it reduces reflection by orders of magnitude relative to the uncorrected standard approach. In addition, at the energy where we made those WKB corrections, it's exactly reflection free. So there's one energy where there's no reflection at all. And in addition, if we compare it to a sort of state of the art method that turns out to be, we found out that you can relate it to WKB corrections in physical behavior. This, by adding the Coulomb potential, you also reduce reflection by an order of magnitude relative to the state of the art method. So here on the left, I'm showing what happens for free particle collisions. This is only looking at the effects of the cap. So without the corrections, you see that reflection is nearly 1 at the lowest energy of interest, which isn't, and you can see that our method, which is the orange, is nearly 0 over all the energies studied. And on the right, I'm showing a model of an ultracold potassium-potassium collision. So you can see that it's quite high error in the uncorrected case, so this black line. And with all of our corrections, it's nearly 0 at all energies. And here at the bottom at the lowest energy, this is in the ultra-cold regime. You can see it works over a huge range of energies. And so looking at this, it looks sort of, might look sort of simple because it's like 2 small changes to the uncorrected potential, and then it's reflection-free or reduced reflection over many orders of magnitude. But the reason this is interesting is that if we look at past attempts, they're often quite involved and still have a lot of reflection, especially over many orders of magnitude. But here we've gotten a simple approach that with very small changes that are totally based on like physical principles, now we're able to get very low reflection solutions. And this is also important today because since it absorbs the wave function over a broad range of energy, it suggests it would work in multi-dimensional wave packet simulations. So for example, we're interested in the ultra-cold potassium rubidium reaction where you have 2 potassium rubidium dimers that come together into a collision complex and then break apart into 14 Kelvin products of K2 and Rb2. And so if we look at like a 2D representation of that potential, you could see that if you have some wave packet in the potential, depending on its motion, it can hit the complex absorbing potential, which is the circle at the outer edge, in many different angles. So it'll need to absorb parts of the wave function with different amounts of radial energy. So it's going to need to absorb in a whole range of different energies. So the fact that our method absorbs over a range of energy suggests it would be useful for these kind of multidimensional applications. And in addition, since the Coulomb potential, or since the WKV corrections are very local and the Coulomb potential, you can sort of restrict its extent with the switching function, it suggests that the method reduces the amount of position space that you need to simulate, which would be especially beneficial to ward off the cursive dimensionality. And as a side note, it actually has an unexpected application because here we were thinking only about the idea of reflection of a wave function from an artificial boundary condition, the complex absorbing potential. But you could also think about reflection into a channel in like an open channel system. So I was hearing about the research of Doug Stone at Yale Quantum Institute of the idea of an optics of these reflection-free scattering modes, reflectionless scattering modes. So the idea is you have some wave functions come in, only into some sort of scatterer or some cavity resonator. And you can find solutions that come only into certain channels and out of certain channels. So this is sort of like reflectionless systems because since they're only coming in on certain channels, they're not coming out of that same channel. So that's a kind of reflection. And so he developed ways to find these reflection modes in different kinds of optical systems. But I realized that you could actually see this as a kind of chemical reaction where now instead of having physical channels that are like your wave guides of your cavity, you could also have channels in a chemical reaction of say different states of a harmonic oscillator of a molecule. And so I realized that this theory that he uses called temporal coupled mode theory, it actually is directly related to the Bright-Wigner theory that we use for quantum systems or chemical systems. So I'm working with him to develop these methods where you would have 0% like reflection of reactants and 100% product formation. So with that, I'd like to thank the professors that I work with, Victor Batista, Rick Heller, Steve Gervin, Doug Stone, and Eric T.J. Nibbering, and as well as Paul Bergold and Cobra and Abenaki for their help on these, they're working on these projects, and also these funding sources, and you for your attention. Thank you.
Thank you very much. That was fantastic. So I will stop the recording.